Hello, 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 hello. Am I audible? Hello, 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 hello. Okay, guys. So let us start. If everything is all right. So we will start. We have started with mathematical methods. There are total 9 units in your CSIR-NET Physical Sciences syllabus, and you always start with mathematical methods, because there are some techniques in mathematical methods which are very necessary to understand if you want to cover other subjects like quantum mechanics, classical mechanics, whatever subjects you cover. You first need the basis. Okay, mathematical methods gives you. So in this course we have already uploaded 4 lectures on vector analysis. Okay, so we have started with mathematical physics, and in the mathematical physics we have uploaded the lectures for dimensional analysis, 1 lecture for dimensional analysis, then lecture 2 to lecture 4 vector analysis. These are very simple topic, easy topics, you can easily understand. And today we will be discussing lecture 5 vector analysis part 1. This is the last part of vector. So in total 4 lectures we are covering the vector part. Now before I go, let me tell you what you will find in the course folder. Okay, we have uploaded or revamped actually the course folder. So we have added this short notes section separately. So as we proceed with the course, as we cover different subjects, we will keep on uploading these short notes. Okay, so for the timing we have uploaded the short notes for mathematical methods, because we will be covering mathematical methods. And second thing I have added there, textbook, standard textbook, standard textbooks. So these all you will get if you go to the course folder, or the course you have purchased. In the course folder you will get these folders. So in the standard textbook, for each subject you need at least 1 or 2 books. So keeping that in mind, for each and every subject starting from mathematical methods to particle physics, for each subject I have added 1 book or 2 books. Okay, so that you can also download. And guys, everything is all right now? Tell me. And if you have any question you can ask me. And this is a live class, and after this live class this recording of this video and as well as the PDFs will be uploaded into your course folder. So if you do not want to miss anything, you will just check the course folder. Whatever things we will do, everything will be uploaded in the course folder, which you can see anytime. Okay, these are the 2 things. And thirdly, we are starting from mathematical physics. In the mathematical physics, as I have already told you, 4 lectures have been already uploaded. So if you are watching this lecture for the first time, you can watch the previous lectures. Lecture 1 give you dimensional analysis, lecture 2 to 4, so there are three videos on vector analysis, and today we will be taking the lecture 5, that will be the vector part 4. Okay, and what I was thinking of telling you. Okay, fourth one, which will talk about assignments. Assignments, there is a separate folder for assignment. So what you will be doing, let's say we are now in preparation the assignments for dimension analysis. So let's say mathematical method. So assignment number 1.1. Okay, this will be your assignment on dimension analysis. Then we will go for 1.2. 1 means this is the subject, first subject, mathematical physics. So this is the number of assignment, dimension analysis. Then we will give you assignment on vector, then matrices, and so on. For classical mechanics, it will start from like 2.1, 2.2, 2.3, then so on, 9.1, 9.2, 9.3, and in this way assignments will be uploaded. Okay, now see assignments. Let's say there will be 10 question or 15 question or 20 question depending on the topic which we are discussing. Let's say for the time being, I'm just giving an example, 20 questions are there in the assignment. So out of this 20 questions, mostly we'll try to cover those questions in the lecture. Okay, we'll incorporate those questions in the lecture. Let's say I give you the solution, detailed solution while taking the lecture. Let's say 15 questions, and 5 questions will be there which you have to try by yourself. I'm just giving you, it may be 10 plus 10 also, 10 question I give you in the lecture, 10 plus and another 10 in the assignment. Although I will upload the PDF solutions, but you will try, and in the assignment there will be some answer key also. Okay, so in this way we will proceed as we keep on completing the topics, the assignments, related assignments will keep on getting uploaded in the course folder. You will get everything in the course folder. Okay, any doubts, guys? And if you also have any suggestion, you can also give me. If things can be better in any way, if you think any point, you can suggest me. I will definitely try to incorporate. And other than that, okay, another component which I have not added, but will try to take 4 tests a month, right? 4 tests a month, like in every week, preferably on Sunday, maybe some 10 AM you can give a test. It will the number of question in the Sunday test will depend, like whatever portion we cover. If you cover a small portion, then number of question will be less, let's say 10 or 15, 20, 30, depending on how much we cover in the previous week. Okay, so this is about this course folder and all. Now let's start with our actual discussion. Today is like an introductory class, and in the first 4 lecture we have covered significant portion of the vector analysis. I have already uploaded the video PDFs, you can watch it, and last portion of this vector analysis left. In that portion we will be talking about the linear dependency and linear independency. Okay, let's start. Any question, guys? You can ask. And let me tell you another thing about the doubt clearing. You can ask during the live classes, or you can WhatsApp in the group, or you can personally DM me also anytime. Okay, whenever I will be able to reply, I will reply. Okay, if you don't have any question, let's start with this linear dependency of vectors. So you must have seen 1 or 2 questions based on this topic, linear dependency and linear independency. So what do we understand by this? You know, by simple term, whether some vectors are linearly dependent or independent, if you can express one vector in terms of other vectors, then they are linearly dependent vectors. If you cannot, then that is linearly independent. Okay, linearly independent set of vectors means you cannot express one vector in terms of the others. So let's say if you have 3 vectors, okay, 3 vectors, we have u, v and w. So these are 3 vectors, so they each vector will have 3 components, x, y, z components. So these 3 vectors, if you are given, they will be linearly independent. Under what condition they will be linearly independent? Linearly independent if they satisfy this criteria. Let's say some constant alpha 1 times u plus alpha 2 times v plus alpha 3 times w, if this is 0, okay, where this alpha 1, alpha 2, alpha 3 are all 0. So if you see, if this condition gets satisfied, that if you take alpha 1 u, alpha 2 v, alpha 3 w, if you want to make it 0, there should be only one possibility, that you choose alpha 1 equals to 0, alpha 2 equals to 0 and alpha 3 equals to 0. Then u, v and w will be called linearly independent vectors. And when you understand that these vectors are linearly independent vectors, those vectors will form the basis. Basis means what? Like if you take the case of your Cartesian coordinates, I cap, j cap, k cap, these three vectors are linearly independent vectors. You cannot express I in terms of j or k, you cannot express j in terms of I cap or k cap, or you cannot express k cap in terms of I cap and j cap. So I cap, j cap and k cap, they are linearly independent vectors and they are said to span the space. What is the meaning of span the space? Spanning the space means with the help of those vectors you can express any vectors. Okay, so this is the theoretical perspective, that you need to have alpha 1, alpha 2, alpha 3 all to be 0. Okay, now write another line, and they form the basis of, this is the real space, real three-dimensional space. What is the meaning? Form the basis, meaning that any vector in R3 space can be written as the linear combination of u, v and w respectively. Okay, so this part is okay. If someone asks you what is the condition of linear dependent or linear independent, you can state this. Now the question is how to check. This is for your exam purpose. In your examination you must have seen many questions. How to check whether the set of vectors are linearly independent or dependent. Okay, how can you check? So there is a simple technique to check this. You see, what you have to do, you have to find out the scalar triple product. The scalar triple product. Scalar triple product is formed by three vectors, right? Scalar triple product. What is the value of scalar triple product? We have already defined in the previous lectures of vectors. Scalar triple products of three vectors, let's say u, v and w you have, then the scalar triple product will be u dot v cross w, right? This is your scalar triple product, and you know the value of this. How to get the value? It is the determinant. What you have to do, you have to write the components of u. So if you have u, what are the components of u? Is u1, u2, u3, isn't it? So it is like u1 x cap or I cap plus u2 y cap plus u3 z cap, right? Similarly, you can also write v, V is equals to V1 x cap, V2 V is equals to, you can write, I am just writing in this way, V1 V2 V3, okay, and W W1 W2 W3. These are components. So you can express it in terms of this also. So U dot V cross W will be your, you just need to write the components row wise, U1 U2 U3 sorry, V1 V2 V3, and for W this is W1 W2 W3. So this determinant is formed if you find it not equals to 0. Remember, if it is not equals to 0, then we call it, this is the criteria for linearly independent vectors. So if the determinant is found to be not equals to 0, it is linearly independent. If it is 0, then linearly dependent vectors. Understood? Now there are two very important things, orthogonal vectors and orthonormal vectors. Let us talk about them. Look, these concepts are very simple, but you need to have the understanding of the fine difference between different terms like orthogonal vectors, orthonormal vectors. They are not same. There is a slight difference between them. So let's talk about orthogonal vectors. If I talk about in simple terms, what is orthogonal vector? What are orthogonal vectors actually? So if the dot product is 0, like normal vector you have A dot B is equals to 0, then we can call them orthogonal vectors. So let's just write the definition. We say that two vectors, numeric 2 is looking odd, two vectors are orthogonal if they are perpendicular to each other. Now if two vectors are perpendicular to each other, their dot product will be 0. You see that we say that two vectors are orthogonal if they are perpendicular to each other. That is, how do you determine? The dot product of the two vectors is 0. So whenever you will be asked whether the given set of vectors are orthogonal or not, you will just take the dot product. This is the first definition. Now let's talk about orthonormal vectors. Orthonormal vectors. So we can understand it by looking at the name carefully. Orthonormal. So it is like combination of orthogonal plus normalized. So for orthonormal vectors, the conditions will be orthogonal, that is the previous condition, plus each vector will be normalized to unity. Normalized to unity, you understood? So let's talk about, we say that again, a set of vectors. We'll do some example, don't worry, you will understand it. Let's say V1, V2 and so on. Let's say n number of vectors are there. So in your examination they may give you 2 vectors or a set of 3 vectors. Now when we talk about multiple vectors more than 3, 4, 5, so we use this term mutually orthogonal. Mutually orthogonal. So it is like एक दूसरे के साथ orthogonal, mutually orthogonal. We say that a set of vectors are mutually orthogonal if every pair of vectors is orthogonal. Okay. In common terms, if you can see v1, v2, v3 and so on. So any vector you can denote by vi. Any pair will be vi dot vj. Let's say if you choose I equals to 1, j equals to 2, then it will be v1 and v2, dot product between v1 and v2. If you take v2 and v3, then it will be I is equals to 2, j equals to 3. So vi dot vj, this is for general dot product for any pair. It should be 0 for all I not equals to j. So it is like it is saying that you cannot take the dot product of vi, v1 and v1, v2 or v2. They should be different. Okay. So okay, orthonormal. This is not orthonormal now. So this is under orthogonal vectors only. Sorry for this. It is like another part of it. This is for 2 vectors. This is for more than 2 vectors. So we'll come to the orthonormal vectors after this. Let's take an example. Let's say we are given this set of vectors. Let's say 1, 0, minus 1. This is one vector. This is v1. 1, root 2, 1. This is, let's say, v2. And 1 minus root 2, 1. Can you check whether they are mutually orthogonal or not? Are they mutually orthogonal? Please do and let me know. Are they mutually orthogonal? Like if you take the dot product 1, 0, minus 1, you can write it in terms of vector. Then you can check dot product 1, root 2, 1. Dot product means 1 into 1, 0 into root 2, minus 1 into 1 and plus. So it is 1 plus 0 minus 1. So this is 0. If you take the dot product between 1, 0, minus 1 and 1 minus root 2, 1, again you find it 1, 0, minus 1, that is 0. And if you take the dot product 1, root 2, 1 dot 1 minus root 2, 1, then it is 1, minus 2 plus 1. So again it is 0. So you see, you take any pair and you take the dot product, it will give you 0. It means these vectors, the set of vectors, this and this is mutually orthogonal. Understood? When we talk about only orthogonal, means it is between 2 vectors. Mutually orthogonal means you have to consider set of vectors and each pair of vectors will be mutually orthogonal separately. Now if this is done, we can go for orthonormal vectors. So let's go for the definition. A set of vectors S is orthonormal. Set of vectors S means, in this way you can consider v1, v2, v3 and so on. If every vector in S has a magnitude of 1, so this is normalized, magnitudes to normalized to unity, and the set of vectors are mutually orthogonal. So let us check the previous example which we considered. Okay, so let's say we have v1, sorry guys, 1 0 minus 1, v2, let's say another vector 1 root 2 1, and v3 what we had 1 minus root 2 plus 1. So the set of vectors are mutually orthogonal, which we have already seen. Okay, now let's check whether they are normalized or not. So obviously they are not normalized. If you take square root of 1 square plus 0 square minus 1 square, then that is not 1. v2 is also not equals to 1. You know how to find out the magnitude. Let's say if you have a vector like this, a vector ax I cap plus ay j cap plus az k cap. How do you find out the magnitude? Magnitude is found out by taking the square root of the component square, summation of component square, ax square, ay square, az square. This is the way you find out the magnitude of a vector. Same goes for here. If you consider this v1, v2 or v3, none of them are having a magnitude of 1. But what you can do, let's say I am defining another set of vectors. Let's say u1 is v1 by modulus of v1. What do you expect? It's a unit vector along v1 direction, so it must be 1, and you will see it will become 1. So what is the modulus of v1? Root over 1 square plus 1 square, so root over 2. So it is 1 upon root 2, 1 0 minus 1. So what you get? 1 upon root 2, 0 minus 1 upon root 2. Now if you take the magnitude of u1, obviously you will get 1, right? 1 by root 2 whole square plus 0 square plus minus 1 by root 2 whole square. Now it is giving you 1. So this u1 is normalized. Now u2, it is, let's call it v2. So vector v2 by modulus of v2. Similarly, what you get? You see, what is the magnitude here? Root over 1 square plus root 2 square plus 1 square. So this is 1 root over 4. So 1 by 2 will come here. 1 root 2 1. Okay. 1 by 2, 1 by root 2, 1 by 2. Again, if you calculate the magnitude, it will give you 1. Similarly, it goes for a vector sign missing. v3, vector v3 by modulus of v3. Again, you will get 1 by 2, 1 minus root 2, 1 1 by 2 minus 1 by root 2 1 by 2. Again, if you calculate the magnitude, you will get 1. So, to check whether the given vectors are orthonormal vectors, you have to consider the magnitude, that should be 1, and they should be mutually orthogonal. These two criteria needs to be fulfilled. Now we can say that the set of vectors v1, sorry, what we have written, u1, u2 and u3 करते हैं, u1, u2, u3. are orthonormal, but not v1, v2, v3 are orthonormal, although they are not although they are orthogonal, but they are not orthonormal. Okay, so I hope you have understood. Just hold on a moment. Now, if I say another line, okay, question came. Okay, one line I would like to give, but I don't have space. Anyways, if you have a space, you can write after it. Okay, then we'll go for this problem. An orthogonal set of non-zero vectors is linearly independent. So, if you consider v1, v2 and v3, then they will be linearly independent. So, as I told you, what is the condition for linearly independent? What was the condition? In the first slide, we have talked about it, u dot v cross w. So, if you can check whether these vectors are linearly independent or not, what you have to check? v1 dot v2 cross v3, है ना? v1 dot v2 cross v3. So, what you have to check? 1 0 minus 1, 1 root 2 1, 1 minus root 2 1. So, what we have done? We have just write the components 1 0 minus 1, 1 root 2 1, 1 minus root 2 1 along the rows. Okay. So, if you find out the determinant, what you get? 1, here it is root 2 plus root 2 and 0 minus 1 minus root 2 minus root 2. So, obviously, this is not equals to 0. So, if this is not equals to 0, then we can say v1, v2, v3 are linearly independent. That is why v1, v2, v3 are orthogonal set. An orthogonal set of non-zero vectors is linearly independent. They are not zero vectors. Understood? So, I hope you have clearly understood the condition for linearly independent, linearly dependent, orthogonal, orthonormal and normalized. These are the few things. Now, you can answer any question. Okay, let's take this first question. Identify the correct statement for the following vectors: A is equals to this and B is equals to this. The vectors A, B are linearly independent, linearly dependent, orthogonal, normalized. Tell me which one is correct. Do it quickly. Look, although we will be uploading these videos in the recorded form in the course folder, you should attend these classes live. Then you can learn it in a systematic way. Okay, and if you have any doubt, you can ask. So you have to check these criteria. Let us try to find out. Firstly, what is given? We are given two vectors. One is, so what are the given vectors? A is given to you 3i plus 2j cap, 3i cap plus 2j cap, and B is given to you I cap plus 2j cap. So first of all, let's check whether they are normalized or not. A, B are normalized. So check. Modulus of A is root over 3 square plus 2 square. So obviously this is not equals to 1. So A is not normalized. And if you talk about B, so this is root over 1 square plus 2 square. This is also not equals to 1. So A, B are not normalized. So fourth option is incorrect. Orthogonal, you can check. They are not orthogonal. They are not orthogonal actually. If you take the dot product to check orthogonality, dot product is 3 plus 4, 7. That is not equals to 0. So that is A, B are not orthogonal. A and B are not. So this is the first problem. That is why I am showing you how to do each thing. Now let's check the linearly independent or being dependent. So what you have to do. You have to just, for 2 dimension, what you have to do, you have to just write the components of the vectors row along the row 3, 2, 1, 2, as you can see. So this is 6 minus 2, that is 4. 4 is not equals to 0. If it is not equals to 0, means A and B are linearly independent. So the first option is the correct option. Understood? If this is done, let us move to the next question. Let E1, E2 and E3 vectors are given. Let S is a set of vectors consisting of E1, E2 and E3. Let R3, this is a real space. R3 denote the three-dimensional real vector space. Which one of the following is correct? You can let me know the answer in the comment section. S is a linearly dependent set, or S is an orthonormal set, S is a basis for R3, or this criteria is getting satisfied. A, B, or C, or D? Which one is correct? Are you able to do it? Look, this is clearly seen 1 0 0 1 1 0. So this is not normalized to unity. This is also not normalized to unity. This is also although normalized to unity, but overall set S is an orthonormal. So this is incorrect. You can directly eliminate this. Now, if you can determine whether it is linearly independent or dependent, then you can eliminate one of these two. So option, because only one option is correct, so the correct option must be from these two, A and C, isn't it? If it is linearly independent, then that will be basis for R3. If it is dependent, then there is no question, option A will be correct. So let us check whether the given set of vectors are linearly independent or not. So what we have to do to check? We have to form the scalar triple product E1 dot E2 cross E3, and you need to just write it all the vectors along the row 1 0 0. So we write it along the row 1 1 0. Let me tell you once again, 1 1 0 means it is I cap plus j cap, and this means I cap plus j cap plus k cap. This is the meaning I cap. Okay, 1 0 0 1 1 0 1 1 1. Let's find it out. 1 into 1 minus 0 minus 0 plus 0. This is 1, which is not equals to 0. It means these three vectors are linearly independent, and they can be a basis for R3. Therefore, the given vectors are linearly independent and hence can form a basis for R3. Fine. Let us move to another question. This topic is small, as we are on our first day, so I have taken small topic. After this session, we will start matrix portion, and you will get all the lectures arranged in a proper way inside the course folder, and this recording will be uploaded just after the class. Now give it a try. This next question. Consider the set of vectors, and 4 options are given. They are orthonormal, linearly independent, they form basis, or you can write one vector as a linear combination of the other two. Can you tell me which one is correct? Are they orthonormal? Look, they are normalized, right? You consider the magnitude is 1. Here the magnitude is 1. Here also the magnitude is 1. But are they orthogonal? Orthonormal condition needs to be read by this orthogonal plus normalized. So the second condition, normalized, being satisfied. But are they orthogonal? They are not orthogonal. If you take the dot product, are they orthogonal? No, they are not orthogonal. So the first option is not correct. Now let's check linearly independent or dependent. So look, the concept is simple. I'm just giving you multiple problems just to make you understand one simple fact, that A dot B cross C, this is the way to choose it, way to check it. If you consider this vector is A, this vector is B, and this vector is C, then you can write it in this way: 1 by root 2 1 by root 2 0 0 1 by root 2 1 by root 2 1 by root 2 0 1 by root 2, and if you check this determinant, you will get it not equals to 0. You can do it by yourself. It's a simple thing to check. Actually from here you will get half. Okay, so it will come out to be not equals to 0. So this is linearly independent. This is correct. Now if they are linearly independent, 3 vectors cannot form a basis. This is incorrect. Yeah, they can form a basis. 1 by root 2 1 0 1 1 0 can be written in a linear combination, because they are independent, linearly independent vectors, and no vector can be written in terms of the other two. So this is also incorrect. So option B is the correct option. A is not. You have to find out the correct option, right? So B is the correct option, no? Okay. So one question I am giving you as homework. You can try it at home, and we can discuss the solution in the next class. And I don't think you require any solution for the problem, because you have understood. Okay, so let me just summarize it again. What you need: firstly, to check linear dependency, the scalar triple product should be 0 for linearly dependent and non-zero for linearly independent. Secondly, orthogonal vectors, and mutually orthogonal vectors. When you have more than 2 vectors, mutually orthogonal vectors. So for a set of vectors, each pair should be mutually orthogonal. Then we learned about orthonormal. So I think now the difference is clear between these terms. Okay, now take this problem as homework. You can do it in few seconds, 30-45 seconds you can do it. V1, V2, V3 Which one of the following statement is true for this set of vectors? Orthonormal vectors, orthogonal vectors, linear dependent vector, they can constitute a basis for spanning a 3D real vector space. Okay guys, so this is all for this session. We'll continue our session on the next day. So we have kept the session timing 8 am. Okay, I will share the session links maybe few minutes before in the WhatsApp group for the time being, and after the live sessions the recording and the PDFs will be uploaded in the course folder. From there you can access it anytime. Okay, any question from you guys you can ask, otherwise we'll end up the session. Okay, so if you don't have any queries, we are ending the session here. Thank you very much guys for joining the session, and see you tomorrow at 8 am again. Till then, bye bye, take care. And I will try to upload the assignment as soon as possible. It is under preparation. Okay, chalo, bye.